Here is another example on implicit differentiation with trigonometric functions. So what we have here is sine y plus x, and you can see that y is inside sine, and the same over there, y is inside sine. So we have sine y plus x. And if we treat whatever that is inside as just x, the derivative of sine y plus x is cosine y plus x. But now we've realized that whatever that is inside is a function, and here it is of the type f of x comma y. So the derivative of the inside would be y prime plus 1 minus cosine x minus y multiplied by negative y prime minus 1. Sorry, plus 1. So if I pull a negative out, I would have cosine y plus x times y prime plus 1. We don't have to do it, so y prime plus 1. Plus cosine x minus y times 1 minus y prime equals 1. And that is an implicit equation. And you can see that y prime is sort of trapped in here. So we have to somehow distribute and simplify. So cosine of y plus x times y prime plus cosine of y plus x plus cosine of x minus y minus y prime cosine of x minus y equals 1. Combine the terms with the y primes. We have y prime cosine of y plus x minus y prime cosine of x minus y plus cosine of x minus y plus cosine of x plus y equals 1. I have a y prime in common, so if I pull y prime out, I have cosine of x plus y minus cosine of x minus y. Move the cosine terms to the other side. We have 1 minus cosine x minus y minus cosine x plus y. Divide by that term on both sides. We would have y prime equals 1 minus cosine of x minus y minus cosine of x plus y divided by cosine of x plus y minus cosine of x minus y. Oftentimes, when we do implicit differentiation, we would be in a position such as this one where we can simplify and solve for the derivative of y. But you've got to keep in mind, at the end of the day, that derivative would in fact depend on y itself implicitly. So here is a problem where we have to find the second derivative, and lots of implicit things going on here. So the first derivative what we have here is cosine xy equals 1 plus sine 2x. Going to treat that as just x, so the derivative of cosine xy is minus sine xy, but that is not simply x, rather it is a function of x, so we've got to multiply by the derivative of xy. But keep in mind, we have to use product rule here because x is multiplied to y. In the previous problem, we didn't have to. So if we use product rule, u is x and v is y. U prime would be 1, v prime would be y prime. So product rule u v prime plus v u prime will have x y prime plus y times 1. So we take that and plug it in there. And the derivative of sine 2x is cosine 2x. Don't forget chain rule. Multiplied by 2. So we have negative sine xy multiplied by xy prime plus y times sine xy with a negative x, or negative y, and that would equal to 2 times cosine 2x. It is always best to solve for y prime before we move on to y double prime. So let me multiply both sides by negative. This is a challenging problem. We have a sine xy in common. So I'm going to pull that out and I'll have xy prime plus y equals negative 2 cosine 2x, and divide by sine xy on both sides. Xy prime plus y equals negative 2 cosine 2x divided by sine xy. Move the y to the other side. And divide by x on both sides. Great. So, as I said, this is not an easy problem. It's a lot of implicit differentiation. The use of product rule, quotient rule is about to come up again. So the second derivative, y double prime, involves the derivative of the first term, negative 2 cosine 2x, divided by x times sine xy, minus the derivative of y over x. So let's do this one step at a time. Let's start with the first term, the derivative of negative 2 cosine 2x divided by x sine xy. And of course we have to use quotient rule. The numerator is negative 2 cosine 2x, and the denominator v is x times sine xy. So u prime is negative 2, derivative of cosine 2x is negative sine 2x, chain rule, multiply by the derivative of the inside, we get 2, and that gives us 4 sine 2x. V prime would involve the derivative in terms of the product rule. So u and v. And that would be u v prime, the derivative of sine xy. The derivative of sine xy is cosine xy multiplied by the derivative of whatever that is inside, which is xy. We already know that derivative from this step earlier. So we have xy prime plus y. So we have u prime, v prime, and we are good to go. So the derivative of the first term is v squared, which is the denominator. So x sine xy squared. V, which is x sine xy, multiplied by u prime, which is 4 sine 2x, minus u, which is negative 2 cosine 2x, minus of minus would give you plus, multiplied by v prime, which is cosine xy, times xy prime, plus y. So we have the derivative of the first term This is a good problem for practice when it comes to implicit differentiation. So we have 4 sine 2x, x times sine xy, plus 2 times cosine 2x, cosine xy, multiplied by xy plus y prime, running out of space here, divide the entire thing by x squared, sine squared xy. That's just the derivative of the first term, which is right here. The derivative of the second term, we have to use quotient rule again. U is y, v is x. So v squared, v times u prime is y prime, minus u times v prime, which is simply 1. So we end up having xy prime minus y. So the final answer here for the second derivative is the sum of the first term, whose derivative we have right here, plus the second term, divided by its denominator, and the entire thing will be subtracted by the derivative we found for the second term. And that is the final answer. I don't think you could simplify this further, so it is best we leave it as is. we shouldn't be wasting time trying to simplify that. It's only going to get complicated. This is a great problem for practice on implicit differentiation, product rule, and quotient rule, and chain rule. So here we have a function of y type. So we have to find the derivative. In order to do that, we have to find the derivative of tangent y. Now that is something we already know. We have found that the derivative of tangent y is secant squared y. But we are taking the derivative of the dependent variable, so we have to multiply it by y prime. The right-hand side in this case is easier. So I have u and v, so we could use the product rule, quotient rule. Denominator is v squared. Numerator, v times the derivative of e raised x plus 1, which is e raised x plus 0, minus u multiplied by the derivative of x plus 1, which is 1 plus 0. So that would give us x plus 1 e raised x minus e raised x plus 1 multiplied by 1 divided by x plus 1 squared. We can't simplify in this problem because I see e raised x which might get cancelled. So x e raised x plus e raised x minus e raised x divided by x plus 1 squared. The e raised x will get cancelled. We have x e raised x divided by x plus 1 squared. So y prime times secant squared y is equal to x e raised x divided by x plus 1 squared, which would mean y prime is x e raised x divided by x plus 1 squared multiplied by secant squared y. So I'm just dividing by secant squared y on both sides. And as always, since we are finding the implicit derivative, the derivative also depends on y implicitly, which we can always expect. So y prime depends on y itself implicitly. So here we have another problem on second derivatives, which is good practice. So left hand side we have x times y, right hand side we have e raised xy plus x. The left hand side we have to find the derivative using product rule. So let's start with the left hand side, derivative of x times y. And from the previous problem, we already have that information because we took the derivative of x times y there. So we could directly use that. So we will have x times y prime plus y. The right hand side, we have e raised xy plus x. If I treat all of that as simply x, then the derivative of e raised xy is e raised xy. But because of the implicit nature of e raised xy, which is a function of both x and y, we have to multiply it by the derivative of xy, which is the principle of implicit differentiation. But we know the derivative of x times y from here. So I'm going to plug it directly and find the derivative of y, which is simply y prime. So putting those together, I have xy prime plus y equals e raised xy times xy plus y prime e raised xy plus y prime. We should always move the terms, put them together and simplify. So xy prime, moving all y prime terms to one side, minus y prime e raised xy minus 1 equals e raised xy times xy minus y. That should be minus y prime, sorry. Y prime isn't common, so we'll pull that out. We have x minus e raised xy minus 1 equals e raised xy. I have a y in common, I'll pull that out, minus 1 times y. So the first derivative is x e raised xy minus 1 times y divided by x minus e raised xy minus 1. This is also a great problem for practice on product rule, quotient rule, chain rule, and implicit differentiation. But the nice thing about finding second derivatives in a problem like this is some of the derivatives we already have found. So we can just take that and plug it in the second derivative. So to find the second derivative, we start with the first derivative. We call that u, and that would be v. So u prime is the derivative of the numerator. And we have to use product rule multiple times. So in the numerator, we have another u and v. So for the quotient rule, we have I don't want to call it uv again, so I'm just going to call it as s and t. So s would be x e raised xy minus 1, and t is simply y. S prime, we have to use product rule for the first term, so x times the derivative of e raised xy plus e raised xy times the derivative of x, which is 1. Keep in mind, I'm using product rule. And t prime is simply y prime. So we just found the derivatives of the terms right here using product rule. But we have to find the derivative of u. So what is the derivative of u, which would be u prime equals s times t prime plus t times s prime. We have s already, which is x times e raised xy minus 1 multiplied by t prime, which is y prime, plus t is y multiplied by s prime, which is x e raised xy plus e raised xy. And divide the let's not divide, let's simplify. So y prime times x e raised xy minus 1. I have e raised xy in common, so I could pull that out. Times x plus 1. So that would correspond to u prime, which is the derivative of the numerator. We still have to find the derivative of the denominator, then use quotient rule to find the answer. So we have v, now we have to find v prime. The derivative of x is simply 1. The derivative of e raised xy, we already found that earlier, it's right there. So I'm just going to plug that in. And the derivative of negative 1 is simply 0. So I have v prime as 1 minus e raised xy times xy plus y prime. So finally, y double prime is v u prime minus u v prime divided by v squared. V is x minus e raised xy minus 1 times u prime, which is what we found here, y prime x e raised xy minus 1 plus y e raised xy times x plus 1 minus u is right here. V prime is what we found over there. Divided by v squared, which is x minus e raised xy minus 1. So the second derivative would equal x minus e raised minus, e raised xy minus 1. I have e raised xy in common right there and there. So if I pull that out, I have y prime x minus 1 plus y times x plus 1 multiplied by e raised xy minus the next term, y times x e raised xy minus 1 times the other term, 1 minus e raised xy times xy plus y prime. X minus e raised xy minus 1 squared. Now, of course, I, from experience, know that if I FOIL and simplify, some of the terms will get cancelled. But in a class like this, it is not necessary. You can just leave it as is. If the simplification looks simple, then we can simplify. But in this problem, it is not that simple. It takes a lot of extra work to simplify. So it is best we will just leave it as is. The same rule applied over here, even though we have a huge expression. Some might get cancelled if we use some sort of trigonometric identity and simplify, but it is not necessary. go for simplification if you believe that terms are going to cancel easily. If not, it's just best to leave it as is. So that would be the final answer. So this is a great problem in understanding quotient rule, product rule, chain rule, and implicit differentiation. Another great problem is this one for good practice. This is also a problem meant for good practice with product rule, quotient rule, chain rule, and implicit differentiation.